Hi guys, welcome back to Data Every Day. Today we're looking at a data set of images of Marvel characters. And so we have a train and validation set of images, and both contain 8 different classes, each corresponding to a different character from the Marvel Universe. So we're going to try to predict which character is present in a given image based on the image. So let's hop into the notebook. We're going to use NumPy, Pandas, the path object from pathlib, and os.path for working with the data. And for visualization, we'll use pyplot and seaborn. For just doing the train test split, we'll be using the train test split function from sklearn. For building the model, we'll use TensorFlow, and for analyzing the results, we'll use the confusion matrix and classification report from sklearn. So let's go ahead and import all of that, and the first thing we want to do is get the directory or the path to the directory containing all of our images. So we actually are going to use our own train and validation sets. We're not going to use the pre-defined sets that came with the dataset. So what I want to do is pool all the images in both the train and validation sets into one big data frame. It's going to be a data frame that lists the file paths to each image along with the labels for each image. So we want to get this Marvel folder, which is on top of both the train and validation sets. So we'll call it image_dir and paste that in. Actually, it didn't capture. It's just a bug that sometimes happens. I'll just go and delete the rest of that so we get it. Okay, but I don't want it as a string. I want to turn it into a path object, which allows us to do some nice things with it. So let's go ahead and now create our file data frame. So like I said, we need a data frame with 2 columns, one with the file paths, one with the labels, and that's the format we're going to need if we're passing it in to a Keras image data generator, which is what we'll do. This will be a transfer learning model, so actually I should put up here a pre-trained TensorFlow Keras CNN. Alright, so let's take image_dir. Currently it's a path, and these path objects have a nice function called glob that allows us to use glob expressions to search for files within the directory. So I want to get all JPEG files in any of the subdirectories. So I'm doing double star to mean anything, anything recursively in the folder, followed by something.jpg, like that. And so the double star allows you to go through directories. And this will be a generator object. So we want to turn it into a list to get the actual list of file paths. And you can see here it is. This is the file path to every JPEG image contained within both the validation and train sets. You see valids on top and trains at the bottom. Alright, so let's call this file paths. And labels, to get the labels for each file path, you'll notice the label is actually located right here. It's the parent folder of a given image. It's always going to be the label. So what we can do is map a function in here. We can map a function to file paths to try to capture that parent directory. So there's a nice function. Here, why don't we take one of these as an example. Turn it into a path object. There's a nice function called, it comes from os.path, which we imported earlier, called split. I can take a path object or a string, and it will split the file name off from the rest of the path. From the rest of the path. So then we can just split it and take the first element of that split to just get the parent directory, and then we can split that again. So another os.path.split to split off the label from the rest of the path. So then here we index with 1 to get the second element, and that will give us just the label. So I want to do this for any path, not just this one. So let's say call it x. So for any path x, this should give us the proper label. Okay. So what we'll do is we'll map this function to our file paths. So if we let's take file paths and we'll apply a map to it. So we need a function, and then we're mapping it to file paths. the function we're going to map is this function here. So for every x in file paths, we'll change x to be the label of x, where here x is a single file path. Then when we're done, we'll make that whole map object into a list, and that should just give us the labels for every single example. We'll call this labels. Let's put it up here next to our file paths. Now we have the file paths and labels. I'm going to turn them into pandas series so that we can put them in a data frame. So file paths will now be a series consisting of the file paths. We'll give it a name as well, which can be file path. And for the labels, that will also be a pandas series consisting of labels. The name here will be label. Let's also convert the file paths data type into strings. So right now it's path objects. We're going to need it as strings if we're going to use TensorFlow, if we're going to use Keras as image data generator. Alright, so now we'll take the two file path and labels series and concatenate them together into a single data frame, which we'll call image.df. That will be pandas.concat, file paths, and labels. And we're concatenating on axis 1, which means side by side. Then, let's just take a look at this. So image.df now looks like this. We have the file paths and the labels for each file. And you can see from this they do match up to the actual value in the file path. Alright, so now what to do? Okay, so if we look at the value counts of the label folder, of the label column. So image.df sublabel dot value counts. You can see we have about 700 to 800 examples for each class. And for the sake of the video, for the sake of time, I'm going to reduce the number of images we're using, just so that our training, it doesn't take too long. What I'll do is sample 200 images from each class. This will, I mean, we're not using all the data, but we can speed up the speed of our model, probably at the expense of some accuracy. But we also can fix the class imbalance here, although there isn't much. So what I'll do is create a list called samples. It's an empty list. And what we'll do is, if we take this, we check the unique values in the column. We can iterate through these unique values, call them category. So for every category in this thing, what is happening? Look at this, I'm pasting on the end and it's going to paste at the beginning. Weird. Oh, that was very strange. Alright, for every category, just label. For every category in the unique values, so we're iterating through all the unique values here. For each one, we're going to create a slice, which I'll call category slice, which will consist of just the values from a given class, just the examples from a given class. So we can take image.df and query the data, looking for any instances where label equals, and we can now, let's say, Loki. Then we'll have all the Loki examples. We can change this to Thanos, and we have all the Thanos examples. So we want to do this for any arbitrary category. So up here, the way we reference a environment variable within a query string is with the @ sign. So @category. So whenever label is equal to the category we're on, then this category slice will consist of just the examples containing that label. And then what we'll do is we'll sample this slice. We'll sample 200 examples without replacement from the slice. Give that a random state so we can reproduce the results. And then what we'll do is take this sample. Just give me one sec. Alright, so we should now, after doing this, take the sample and append that to our samples list. So samples.append, and then put those 200 samples in the list of samples. So if we run this, samples should now be a list of data frames, where each data frame in the list contains 200 examples from a given class. You can see we have one for each class. So what we'll do is now concatenate all these data frames together into a single data frame, and we'll just overwrite image.df here. This will be pandas.concat samples and along axis 0. So this time we're putting them on top of each other, so we do axis 0. And then after we concatenate them, let's shuffle them, since they're going to be all ordered. I mean, all of one class will be together like that. So we want to shuffle it up. For this, we can just sample 100% of the data without replacement, which is the same as a shuffle. So fraction equals 1.0, and then give that a random state as well to be able to reproduce the results. Last thing to do is then reset the index, and I'm including drop equals true to prevent the old indices from becoming a new column. Alright, and when that's done, I'd like to just print this out again, the value counts for the data frame, so we can verify that we have 200 of each. So ImageDF now looks like this. We have 1600 rows, that's 200 images for each label, and the data has been shuffled and our indices are in order. So I think we're ready to create our generators. So let's say loading image data. So the purpose of a generator is to load in a batch of images at a time, train on those images, and then recycle the memory so that we don't run out of memory by loading all of the images off the disk at once. So there's one more thing we should do before we do this is I want to do our train test split. So let's use the function from sklearn, and we're going to pass in the ImageDF, and that will split our data into trainDF and testDF. And we're just going to specify a train size. I'll use 70% here, and I'll keep shuffle equals true on. So that will do one more shuffle before we make the split, and give that a random state so that we can reproduce the results. Alright, one thing before we continue, I'm going to enable GPU acceleration here because we are doing image classification. So accelerator GPU, turning that on. Alright, so for the image data, we're going to use tf.keras.preprocessing.image data generator. And so what this will do is, like I said, load in one batch at a time. So when we're defining this now, when we're creating the generator, we're sort of giving a specification to the model. We're explaining to the model how the data should be loaded from the disk. We're not actually loading it into memory. We're just sort of creating a set of rules to pass to the model for how to load it. So let me just run everything before this block, and then we're going to call our first generator train generator. This will be the generator we use for the train set. So we're using a transfer learning model today, and I always just go with MobileNet for the purposes of these videos because it trains really quickly compared to other ones. MobileNet is a lightweight transfer learning model. So what that means is basically the convolutional layers, the feature extraction portion of the model has already been trained. Well, actually the classification aspect has also been trained as well, but we're going to drop that part because we want to use our own classification layers at the end of the model. So here is the pre-trained model. And I should point out that anything we pass into this model needs to be pre-processed in a specific way. And it says here, note, each Keras application expects a specific kind of input pre-processing. For MobileNetV2, call this function on your inputs before passing them into the model. So this function is what we're going to use. The reason I'm bringing it up now, we could, hold on, that's not what I want. I want to grab the actual text. So we could actually use this function. If we look at this, you see it's an actual function. We could run the data through this within our model, but the image data generator allows us to specify a pre-processing function beforehand, and we might as well just do it here. So I'll put the function in to tell the generator to pre-process the images this way before moving on. And you can also specify any image augmentation you like in here. I'm not going to do that for now, but you could. There's a good amount of different augmentations you can apply within this image data generator initialization. Alright, so last thing we specify is a validation split. So we only need this if we're getting our validation images from the same generator, which we are. And then we're going to create another generator. This is going to be our test generator. And for this one, we don't need the validation split. That's it. Now we're going to specify how to actually flow the images from the disk through the generator and into the model. So we use flow from data frame for this. So we take our generator, and our generator has a function called flow from data frame. We could also use flow from directory, but if we want to specify our own train, validation, and test sets, it's best to use data frame. You get a lot more flexibility out of it. So here's where we specify how we'd like to flow it. First, we specify the data frame we'd like to actually target. Here, this is going to be train df, which is what we created earlier, right? We did our train test split. Then we're going to specify the column containing our file paths, which will be the x column. That will be called file path, as we named it earlier. Then our y column, which is the label column, which we named label. Then a target size, so we can actually resize the image here. And the MobileNet model was originally trained on input shape of 224 by 224 by 3. We are able to use a different input shape. We'd have to specify it when we create the model, though. However, we are going to need 3 input channels. And for simplicity, we will keep the same dimensions. So what we'll do here is resize all the images to be 224 by 224. And our color mode will be RGB for the 3 color channels. Then we'll specify a class mode, and this is categorical. That just means multi-class. Our batch size can be 32, so we can specify the batch size here so we don't have to specify it later in the model, in the fit function. Then we include shuffle equals true. Since we're training, we always want to shuffle the data so the data doesn't memorize. And then we'll give it a seed. So this is just a random state, so we can reproduce the results. And the subset, this can either be training or validation, and is only a valid argument when you have given it a validation split. So if you have it as validation, it'll take the 20%, and if you do it as training, it'll take the 80%, the other 80%. Alright, and then this whole thing provides the specification for how to get the train images. So I'll go ahead and call that train images. Then we'll copy this over, and now I want to get our validation images, so I'll call it val images. The only difference is the subset is validation. We're still taking from the same generator using the same data frame, but we're taking a different subset of the data. Then we'll do the last one. This is test images, and for this one we're actually going to use the other generator, our test generator, so we'll change that here. And we're flowing from the test df instead of train df. We also don't need a subset or a seed, and we should set shuffle to false. Since we don't want to shuffle the test images, since we're only evaluating on them, we want to keep the order the same. Alright, let's run this, and we should see how many we have in each set of the data. So 896 training examples, 224 validation, and 480 test, and they all belong to 8 different classes. So now we'll start training. So first let's get our pre-trained model. So this is tf.keras.applications.mobileNetV2, and we should specify a few things. So the input shape, this is really, we don't have to specify it if we're using the default shape, but we'll do it anyway, which is 224 by 224 by 3. Then alpha, we don't have to worry about that. This is the width of the network. We're just going to keep it as it is. And then include top equals false. We want to make it false. So include top. The top of a network is usually that's what the output is referred to. So the final most layers will be the top of the network. And here we want to not use the top that's already comes with the model, because we want to use our own top, or our own output, to give us 8 different probability values, one for each of the classes. This model was originally trained on the ImageNet dataset, which has 1,000 classes. So you can see you can actually specify your own classification in here, change the classes as you like. We're not going to do that. We're going to just construct those layers ourselves. But yeah, so we have include top equals false, weights equals ImageNet. I'll just include that so we know, but that's the default value. So we're keeping the weights the same as it was originally trained on. And then last one I want is pooling. So pooling just allows us to put our own, automatically put a pooling layer onto the end of the model, the top of the model. And the pooling layer, if we're doing average pooling, it's going to be a global average pooling, which means we'll end up with a one-dimensional output instead of 3-dimensional, or I think it's 3-dimensional. Let's just see that. Take the summary of this. You can see the summary. Go all the way to the end. Yeah, it's 3-dimensional, and then that gets average pooled down into 1 dimension. So we end up with 1,280 features that have been extracted from the original image. Now you'll notice right now the trainable parameters, there's 2 million of them. We want to make sure that all of these parameters are not trainable. So what we'll do, let's just store this whole application in pre-trained model, and then set pre-trained model dot trainable to false. Then let's look at the summary. If we go down to the bottom now, there are 0 trainable parameters. So everything is sort of locked in as it is, because we're going to use the same parameters, the same weights, as were learned by the original training of the model on the ImageNet dataset. Okay, so now we'll construct the rest of the model. So this is the feature extraction portion. This is designed to take features from the image, convert spatial relationships between pixels into informative features. So we'll take the pre-trained model dot input and use that as our inputs, and then we'll use from here. Remember this. The output of our pre-trained model is just 1,280 features. So we'll use those 1,280 features as the input to like a standard neural network. So that will have 2 hidden layers, which will be dense layers. Let's give them 128 neurons with a ReLU activation function. And then we don't want to pass in inputs here. That would just pass in the input of the pre-trained model. We want to pass in the output of the pre-trained model. So pre-trained model.output. And then we'll just duplicate this, and instead at the end we'll pass in x. Then we'll have the output of our whole model, which will be tf.keras.layers.dense again. Here we output 8 values, 1 for each class, and a softmax activation function, so that they become probability values between 0 and 1, such that they all sum to 1. Then we'll create our model with tf.keras.model, specifying the inputs and outputs as we have them above. And then we'll compile the model. So we'll use an atom optimizer. And for our loss function, we're going to use categorical cross entropy. So the way to know if you should use sparse categorical cross entropy or just regular categorical cross entropy is you look at the train images, or whichever your data is in, and you look at the labels. So actually, if I look at the labels here, it's going to give me the labels as integers. But if I want to see how the data is actually coming in, I'm going to take the next batch using the next function. And then you can subscript the next batch with 0 to get the image data, or with 1 to get the label data. So let's do 1 to see the labels. And you can see that each label is actually being encoded as a vector. And when it comes in as a one-hot vector, you should always have categorical cross entropy. The reason it's not sparse is because technically you could have multiple ones in here, but when it comes in as just an integer, when it gets converted into a one-hot vector, it's guaranteed to be sparse. So that's why you'd use sparse. Alright, so categorical cross entropy, and then we'll just use accuracy as our metric since it's multi-class. Don't have many options. And then for history, we'll fit the model. So we'll store the result of the fit in history. We're going to train on the train images. And our validation data is going to be val images. Then we'll specify a number of epochs. So let's train for 100 epochs. And then give it a callback. So this will be tf.keras.callbacks.early stopping. So we're going to watch the model. We're going to watch the validation loss. And we'll give it a patience value of 3. So after 3 consecutive epochs of no improvement in the validation loss, we'll stop the model. We'll stop the training and restore the weights from the best epoch. So restore best weights equals true. Alright, let's run this. So we do have GPU acceleration on. Okay. So while that goes, let's just start writing up the results. So I want to get a confusion matrix and classification report for the data, as well as outputting the accuracy on the test set. So let's get some results using model.evaluate. That will return the loss and accuracy on whatever set we pass in. So let's pass in test images, and I'm going to set verbose equals 0 so we don't see the loading bar like we're seeing here. Alright, and then we'll get a set of predictions as well. For this we use model.predict on the test images. But the predict function will return whatever the output of our model is. In this case, it's going to return 8 probability values. We really want it to return 1 integer. So the classification is given by which of the 8 probability values is highest. So because the highest probability is going to be the class that we're predicting. So the way we can get the highest probability is just by taking the max across axis 1, numpy.max across axis 1. But we don't actually want the highest probability. We want the location of the highest probability, or the index of the highest probability, which will be the actual class. So we'll use the argmax function to get that. Alright, then we'll get some class names. And the class name should come from test images dot class indices. So the class indices is a dictionary that comes along with the images. And it gives you the mapping from the original name of the model to the integer encoding of the label. Sorry, name of the label, not name of the model. So we just want the keys. The keys of this dictionary will be the actual strings of the original values. Oh, it looks like we finished, so I can show you. Alright, let's look at class indices. You can see it's mapping the string to the integer, and if we get the keys from this dictionary, we'll just get the actual labels, and in the right order as well. So let's turn that into a list, and then use that as the class names. Alright, now we'll get our confusion matrix. So this is a function from sklearn, and we just pass in the true values and the predicted values. The true values we can get from test images.labels. The predicted values we can get from predictions. Now I'm also going to specify the order of the labels to use. It's probably the default to use ascending integers, but I just want to be absolutely sure we have the right label ordering. So I'm going to use a numpy a range of 8 values, which really is the same as just saying would be the values of this thing. I guess we could use that as well, but this is the same thing if we just look. Same thing, but just as a numpy array. So then we'll get our classification report. So let's call this one CM, and then we'll create a classification report, which we'll call CLR. And that's using the function from sklearn as well. Here we pass in the real values and the predictions again. We also specify the labels the same way. But here we actually are going to be seeing the names, so we want to use the class names. So let's say target names equals class names. Alright, now we'll print out the test accuracy. Display this to 2 decimal places as a %, and format this using results, which is what we have up here, sub 1. So the second value from results will be the accuracy value, and then I'm going to multiply it by 100 so that we see it as a %. Then we'll display the confusion matrix. So I'll go to figure size of 8 by 8. And we'll use the Seaborn heat map function to plot that, passing in CM, turning on annotations, formatting like format G so that we see it as integers and not scientific notation, setting the minimum color value to 0, giving it a blues color map, and turning off the color bar. Then we'll set some tick marks. So for the ticks, the actual ticks will be the spacing of the tick marks. So we can use another NumPy A range to get that, and then shift it over by 0.5 so that the tick marks end up in the middle of each box instead of on the corners. Then we'll give it the labels, and this will be the same as class names. Then we also want to rotate them so that they don't overlap. So I'll rotate by 90 degrees for the X, copy this over, do exactly the same thing for the Y, but rotate 0 degrees for the Y. Alright, then we'll give some axis labels. So predicted on the X, and for the Y will be actual. And we'll give a title, which will be confusion matrix, and we'll show. Last thing to do is then just print out the classification report. Alright, let's take a look. Just take a moment while it loads up. It's taking a while. Alright, there we go. 61% accuracy, and you can see the model is doing fairly well. Not too many misclassifications, and where we do have misclassifications, it's pretty spread out across all classes. Maybe a little bit concentrated here, but not really. Yeah, it's looking pretty good. I mean, we are misclassifying a bit. You can see our F1 scores are on average in the 0.6 range. But no one F1 score is doing much worse than the others, and no one is doing much better than the others. The best one here would be Spider-Man, which would be the highest F1 score. So the F1 score is just a combination of precision and recall. Precision is just saying out of all the predictions you made for a given class, how many did you get right? What % did you get right? And recall is saying out of all the actual values in the class, out of all the actual training examples, how many did you get right? What %? Alright, and so that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.